So let's start with L2 regularization. So I've seen this before. So all of you see that this is L2 regularization, right? What does L2 regularization does? Now tell me, in the context of things that we have discussed today, what is this? Empirical estimate of the train error, okay? And what is this? Is that fine? Right? So everything that we are going to write is L, because of it's W, but fine, right? Okay. Now, why does this relate to model complexity? What am I doing here actually by adding this? So we are going to see a very detailed analysis of this, but I just want to see first whether you get an intuition behind this. So by doing that, what you are trying to do? Not allow the model to become very complex, right? You don't want a model where your weights can take any possible value. You just want the weights to be small. So you're reducing the freedom on the model, right? Less freedom, less complex. Do you get the intuition at least? We'll see this in more detail, but at least you get the intuition why we are doing this. So we are using omega, remember that we are using this omega theta as a surrogate for model complexity. So if you add something in omega theta, just make sure you understand that this relates to model complexity, okay? Fine. And now for SGD, what would I need for gradient descent? Just in case you have forgotten what GD is. What do we need? Nothing, we have done it, ho gaya abhi. Gradient of this, which is a sum of the derivatives of the two quantities of which you know one, right? You know this already. And what's the other guy? Alpha W, right? So you see this L2 regularization, right? One reason why it is preferred is now, imagine you have already written code for gradient descent. All you need to do is change it at one place, add this to your update rule. That's all you need. And you can think of the vector form of this, where you have a vector of parameters. You can think of the matrix form of this, where you have a vector matrix of parameters. All you need to do is add one term to your update rule. So it can be done with very minimalistic change. And this would be your update rule, okay? Now let's see a geometric interpretation of this. Now from here onwards, some of you will start getting a bit uncomfortable with some of the math because of these assumptions that it only works for squared eggs in a vacuum, right? So you'll see those kind of things. I will not tell you upfront what is the assumption I'm making, because that will just spoil the analysis. You'll just not enjoy it as much as you would. Ignorance is bliss, right? So if you don't know what the assumptions are, you'll probably enjoy it more. But for some of you, will pick it up. Just keep it to yourself. At the end, I'll tell you what are the assumptions I have made. Okay? There are some tricky assumptions that I'm going to make, but just live with it and just try to enjoy it while those assumptions last, right? Okay. So now let's assume that W star is the optimal solution for LW. What is LW? The train error, not our regularized error, just the train error, okay? And so if W star is the optimal solution, what can you tell about the derivative with respect to W star, or derivative at W star, sorry? It's going to be 0 from basic calculus, right? So if I say minimize x square, the minima is where derivative of x square with respect to x is equal to 0, right? Everyone knows this, okay? So now consider one point which is, okay, so what I actually want to consider is that, let me just see how to say this. So let's say I'm at W star, okay, and I want to consider some point in the neighborhood of W star, okay, that's what I want to do. So one way of saying it is that H is equal to W minus W star. Is that fine? Okay, so that's what I'm going to use in the next few steps. So suppose I have such an H which is equal to W minus W star. That means I can move from W star to some point in its neighborhood by using H. And what does Taylor series tell us? This is what Taylor series tells us, right? That the value of the function at this neighborhood point is equal to this. All of you know Taylor series well now, right? So is that fine? I don't need to really go over this, right? Everyone is okay with this? This is approximation up to the second term, second order derivative. Now what was H actually? W minus W star. So I'll just substitute that, and this is what I get. Is that fine? What is this quantity? 1, minus 1, 0, infinity, minus infinity, 0, right? We just did that, okay? So that term will disappear. What am I left with? This quantity, okay? And I've forgotten what's next. Okay. Now again I'm interested in the derivative of this, okay? So what will happen if I take the derivative? What will I get? I'm interested in computing grad LW. What will the RHS be? How many of you are fine with this? Remember, this is a quadratic form, right? So this is of the form x square. That's roughly how I remember it. It's not correct. This is of the form x square. So when you take the derivative, one of the x's will disappear. Okay, and this quantity will remain. Okay, so everyone gets this? Okay, so now what do I have is, I have the formula for the gradient with respect to LW, and it is in terms of the gradient with respect to, or rather the gradient at LW star. That's what I have achieved so far. But what am I actually interested in? The regularized loss. What I'm still dealing with is the non-regularized loss. This is just the empirical estimate of the training error. That's not what I'm interested in. I'm interested in the regularized loss. How many of you are lost at this point? Oh, h is the second order derivative. Oh yeah. So these are brackets just for clarity, but I see it's making it more unclear than clear. Yeah, actually we should have used u and then call it u transpose h u. So h, the brackets here are not indicating function. Okay, this is just h transpose h h. Now that I say it, I realize how bad it is. Oh, last step, what are we taking gradients with respect to is w, right? Is it fine? So we have don't get too confused, right? So up till this point, we have a formula for LW, right? And I'm just interested in the derivative of that, okay? And all I've achieved by this is that I have, okay, in fact, I have one more step, right? What is this quantity? 0, okay? So we now know that the derivative of the loss function with respect to W can be written as this quantity. Is it okay? And I've just derived it step by step. There's nothing great about it. Anyone is why I'm doing this is not clear. That will become clear, hopefully. But what I'm doing is clear, right? Is that fine? Can I move ahead? Now what we are actually interested in is this quantity, because this is the true loss that we are going to deal with, right? And we just saw on the previous slide that this quantity, which is on the LHS, is equal to this thing on the RHS. This is what we saw on the previous slide. Can I just go back to the previous slide? Because the derivative of this was just alpha W. Now let's start with this. So on the next slide, okay, let me just see if there's anything else that I need to say here. Okay. So far everyone is clear what I've derived so far. Why is not clear, but what is clear? What is being derived so far? So I have said that the derivative of the loss function, or the regularized loss function, can be written as this quantity. Okay, is that fine? Where W star is the optimal solution for, with respect to the unregularized loss function. Okay, and now what I'm interested in this solution with respect to the regularized loss function. Okay, now let W tilde be that solution for the regularized loss function. So that means the derivative of the regularized loss function at W tilde is going to be 0. Nothing great about this. But I just told you on the previous slide that I can write this quantity as this quantity. That's what we derived on the previous slide. Okay, just take my word, that is what we derived on the previous slide. Okay, no confidence in me. Okay, that's fine. Now are you okay if I write it as this? Just rearranging some terms. Oh, sorry. So I'm just grouping all the W tilde terms, and this is a matrix is needed here, right? Because I can only add 2 matrices. So what I'm just doing is putting the elements across the diagonal. Everyone understands this? Everyone gets this step? Okay. So now I have a formula for W tilde in terms of W star. Okay. I'm going to go a bit further and be a bit bold and compute the inverse also. So now I have an exact formula for W tilde in terms of W star. So what is this relation that I'm trying to establish? Suppose I know the solution with respect to the unregularized loss, and now I have added regularization. What happens to the new solution? So I am telling you, okay, the new solution would be smaller weights and so on. Right? That's what L2 regularization tells you. Now we are just trying to make an interpretation for that. So I've given you a closed form solution that W tilde is actually equal to this quantity that you see on the right hand side. Okay. Why we are doing this is still not clear, but right now just focus on the what part of it. This is just some mathematical steps that I am doing. Anyone who is not comfortable with this? Now notice what would happen if alpha tends to 0. What would be W tilde be? W star. What do you mean by alpha equal to 0? No regularization, right? So that's just one corner case that I want to do, but that's not what we care about. I mean, that's stupid to do all this and tell you that if you don't use regularization, you'll get the same solution. But that's not what I'm going to tell you, right? We are interested in the case when alpha is not equal to 0. Okay, so let's look at that case. Now I'm going to assume that H is a symmetric positive semi-definite matrix, squared egg in a vacuum. Okay, so if that is the case, then I can write H as this. I've just done the dash of H, eigenvalue decomposition of H. Okay, and I know that since it's a squared symmetric matrix, the eigenvalues are going to be orthogonal. Yes, eigenvectors are going to be orthogonal. Okay, and that's why I can write this, that Q transpose is the inverse of Q. Okay, now let's start with whatever we had on the previous slide and substitute what I'm going to substitute. Instead of H, I'm going to use Q lambda Q transpose. Okay, so I'm doing that. So is that okay? I'll just go over the steps and let me know at any point if you have a problem. What I've done is I've replaced this I by this, and it's valid because Q transpose is just equal to I. Okay, I've just taken Q and Q transpose as common, right? So this is ACB plus some AZB. So I've taken A and B out, right? Okay, is that fine? Okay, now what's the next thing I'm going to do? This is of the form ABC inverse. So I'm going to write it as, and the inverses are neat, right? Okay. Is this fine? What will happen to this quantity? I. What is this quantity? Q. And this is what I am left with, but there's still something more I can do, I guess. Let's see. Okay, so I can write this entire thing as a diagonal matrix. How many of you see that it's a diagonal matrix? Because lambda is a diagonal matrix, I of course is a diagonal matrix, I is multiplied by a scalar which is also going to be a diagonal matrix, and the whole thing is again multiplied by some diagonal matrix. Okay, what's the inverse of a diagonal matrix? The reciprocal of the diagonal elements. Okay, good. So it's fine. So I have a very neat formula for what W tilde looks like in terms of W star. Okay, again, why am I doing all this? God knows. But and here D is equal to this quantity. Okay, so what exactly is happening here in terms of linear algebra or in terms of geometric interpretations? Okay, so let me just see if I have to do something first. Okay, so what is happening to W star? It's getting rotated. Remember what happens when a matrix hits a vector? It gets rotated and scaled also. And then what is this diagonal matrix going to do? Scale it, element wise scaling actually. Everyone gets this operation? Okay, and then I am again rotating it by Q. Okay, again the same stupid question. If alpha is equal to 0, what would happen? Q transpose would rotate it by something, and then Q would rotate it back. Right? That means you will end up getting the same solution. Okay, if alpha is equal to 0, we understand. Now if alpha is not equal to 0, first let's see what does this matrix look like. Okay, so what is this matrix actually? It's a diagonal matrix. What are the diagonal elements? What is the first element in the diagonal? 1 by, everyone agrees with this? What's the second element? Okay, fine. And what's the other matrix that I have? Lambda. So D is equal to the product of these two things, right? So what is D going to be? What's the first element of this matrix going to be? How many of you say lambda 1 by 1, lambda 1 plus alpha? This much is clear? Everyone gets this? Okay. So this is a diagonal matrix of the form ABC. Let's consider a 3 by 3 matrix. Okay. Now I'm going to multiply it by another matrix X, Y, Z, which is also a diagonal matrix, right? Because this is also, so this matrix I have already told you what it looks like. The other matrix is also a diagonal matrix. Now what is this product actually? AX, BY, CZ, and everything else as 0. Now everyone gets it? Now can you say what would this product look like? If you can actually make out It would be a diagonal matrix. And what would the diagonal elements be? Is it fine with everyone now? Okay? Is it okay? Fine. So now what is happening? So first this rotation is happening, right? That no one is denying. After rotating, what is happening? This product is actually a vector. That is fine. Okay? What are we doing to every element of the vector? Scaling it. Scaling it by what quantity? These quantities, right? Every element is getting scaled by the corresponding entry in the diagonal, in this diagonal, right? So the first entry is getting scaled by this, the second entry is getting scaled by this, and so on. Okay? I just want you to take some 30 seconds and try to figure out where I am headed from here. Let's see if I can, yeah, maybe look at this sentence and see. First of all, everyone agrees with this sentence, right? Is there anyone who does not agree with this sentence? I'm just trying you to figure out the implication of this sentence. You get it? Some people are nodding their heads. Because if you scale it, right, then there's no guarantee, right? Because the vector has changed. Okay, what happens in the following case? That means that dimension will be left as it is. Okay, but if this condition holds, what would happen? That dimension is almost getting multiplied by a 0, right? So you see these two extremes. When the eigenvalue is very large, you will end up staying where you were. So those dimensions will not be affected. If the eigenvalue is very small, then you're almost getting scaled down to 0. So now what will happen is actually only the significant directions, larger eigenvalues will be retained. So what is the effective number of parameters in your model now? See, remember that this W vector is a vector of all the parameters. What am I telling you? That some of these are going to disappear. When which condition holds? The third bullet holds. Some of these are going to disappear. That means the effective number of parameters which remain in your model is going to be less, right? And you see that it is going to be given by this quantity, right? So that's sometimes known as the effective number of parameters in a neural network. If the effective number of parameters in your neural network is decreasing, that means what you are doing? Making the model less complex, right? So that's what we have achieved. You see that? Okay. Now let me end with a pictorial interpretation of this. You see two figures here. I mean, there's only one figure, but you see two different things here. Can you tell me what this is and what this is? That's the first question I want to ask you. The hint is that in this lecture, we care about the other hint is, what was W star? The solution for the unregularized loss, which means which loss? L theta. Do you need any more hints? Sorry? This box is the contours of L theta. This box, contours of omega theta. So this thing, right? Just ignore this part of the figure for now. Okay. This I have marked as W star. W star was the solution when I only had the unregularized loss. Okay. That was the solution when I had the unregularized loss. Okay. So remember the contour maps that we had seen. So this is the minima of that particular function. So this is the contour map for L theta. That is clear. Now what probably is not clear is, why is this the contour map of omega theta? Let me just go ahead actually. Yeah. Please don't read this. This is the prestige. Okay, so don't please read that. Okay. So this is the contour map of omega theta, right? Because omega theta in what's the minima for omega theta? It's a function of the form W square. What's the minima? 0. And what does that function look like? And what is this point? 0, the origin, right? So that's why this is the contour for omega theta. Okay. Now, what is happening? This was a solution when you had without regularization, and now this is W tilde, which is a solution with regularization. So can you make some commentary on this? With respect to, not just general commentary, with respect to the things that we saw in the derivation. We talked about rotation, scaling, dimension specific scaling. So what is happening? This was my original solution vector. This was my original solution vector when I did not have the regularization term. Now what has happened? Rotation has happened. And we saw that there is a rotation operation happening. More importantly, what has happened? Scaling has happened. More importantly, what has happened? Dimension specific scaling has happened, right? One dimension has not, this dimension has scaled down. This dimension has not scaled down enough. That's exactly what we wanted, right? We wanted the less important weights to go down and the more important weights to stay there. We did not want a uniform scaling down. We wanted a dimension specific scaling down. So the weight vector has been rotated, yes. Each dimension after rotation has been scaled. Some dimensions have been scaled down more, the other dimensions have been scaled down less. How many of you can make this interpretation from the figure? Now that I've told you this interpretation? No, still if you don't, how many of you can still have a doubt with this? You still have a doubt? Okay, what is the doubt? Okay, fine. So, okay. So this was the original solution vector, right? The math told us that what actually happens is, when you add this omega theta, your solution vector gets rotated, okay? At the same time, there is also some scaling down. And that scaling down is per dimension. How many dimensions do you have here? 2 dimensions, right? So this is one dimension, this is the other dimension. Now, in the original case, both these weights actually seem almost equal, right? Right? I mean, if you look at the W1 coordinate and the W2 coordinate, they were same. Now, after this regularization, what has happened is, what are the new coordinates for W1 and W2? This is the coordinate for W1, right? This is the value of W1 and this is the value for W2. Both of them are admittedly smaller than the original values for W1 and W2 in the absence of regularization. Are both of them equally smaller? No. They have been scaled differently. One weight has been scaled down more, the other weight has been scaled down lesser, right? And that's exactly what the math was telling us, that they get scaled in proportion to those lambda 1 by lambda 1 plus alpha, and that's exactly what we see in the figure. Is that fine? How many of you get this interpretation now? Is that okay? Okay. So all of its elements are shrink. You have a question? Yeah. Yeah. So this final resultant, right? It's, so what would have happened is that there would have been first rotation, then scaling down, and then again rotation. So what you're seeing here is the final rotation, right? So it's not, it should have been shown in 3 steps. We're just shown the final step now. Is that okay? So his question was that we first had a rotation, then had a scaling, and then again a rotation. But when I was explaining the figure, I spoke only about one rotation. So I basically clubbed both the rotations. And so what you see finally is rotation, scaling down, and again rotation. Is that fine?